Good afternoon, I'm Ralph Rudd. I'm presenting my PhD proposal called Benchmark Trees. As Professor Turley explained, I'm supervised by Dr. Jörg Kienitz, Associate Professor Thomas McWalter, who's internal here at Duke University, and Professor Eckhard Platen, who is at UTS. Briefly, the main thrust of my research concerns the construction of optimal tree methods to simulate the stylized minimal market model under the benchmark approach. What I do in my written proposal, which you have all at least skimmed or seen, is in the simplest possible case, I derive the growth optimal portfolio and the associated real-world pricing mathematically for a two-asset market, and then I make the appropriate assumption to arrive at the stylized minimal market model, and then I pose my three research questions, one in each of the areas outlined at the bottom here. I want to take a different approach in my proposal presentation. What I want to do with this presentation is place the benchmark approach into its proper context in the world of math finance, then place my research into the context of the benchmark approach, and then finally have a single slide on my first attempt to address this problem, which is in the framework of vector quantization. So even though I have raised a research question in each of these three areas, and in the perfect world you'd be able to complete your theoretical analysis before you begin your numerical analysis, complete your numerical analysis before you begin looking at applications, because of my background I'm more comfortable jumping straight into numerical analysis, and that'll be the focus of this talk. So let's begin. I want to look at the framework or modeling framework of mathematical finance through the lens of arbitrage assumptions. This is of course not the only lens through which we can categorize what we do in financial mathematics. I feel it's a very powerful and special lens, number one because mathematically rigorous definitions of arbitrage are in some way unique to math finance. Secondly, because there is an economic interpretation for each arbitrage assumption that we make, so we can discuss it with people outside of the field. And lastly, because I think you can make the statement that the work by Delban and Schachmeier on the mathematics of arbitrage and the book Mathematics of Arbitrage is fundamental to what we do. So I'm going to briefly go over not the mathematical definitions, but rather the economic or portfolio implications of each of these arbitrage conditions as they are listed, from strongest on the far left to weakest on the far right. This structure that I'm using to talk about arbitrage is due to Claudio Fontana and his paper in 2013. He's from the University of Epsilon. So let's begin. I want to start in the middle here with the concept of no arbitrage, as it was used by Harrison and Pliska and Harrison and Krebs. The concept of no arbitrage is the one that we're most familiar with, and it's the first concept that we're introduced to in mathematical finance. This essentially states that it should be impossible to construct a zero-cost self-financing portfolio that has no probability of a negative payoff and a positive probability of a positive payoff. This is what we exclude when we make the no arbitrage assumption. Delban and Schachmeier had to strengthen this by essentially including what are known as epsilon delta arbitrages. You want to exclude the possibility of taking on a very small amount of risk for the positive probability of a profit. This doesn't really have an economical interpretation, but is rather a mathematical construct that's necessary to show that we have this existence of an equivalent martingale measure. If we move further to the right, we have three equivalent notions of no arbitrage. I'm going to just talk about the nomenclature as I go. So no arbitrage of the first kind is what it's called by Fontana in his paper. No unbounded profit with bounded risk is what it's called by Karatsas and Carderas in their 2007 paper. And no cheap thrills is what it's called by Leuvenstein and Williard. This is obviously a weaker condition than no arbitrage. What this condition states is there cannot exist a random variable that has some positive probability of a positive value that can be super replicated by every market participant regardless of their initial wealth.
So you didn't define NFLL.
No free lunch with vanishing risk.
Okay. It used to be called no cheap snacks rather than no cheap thrills.
And I've also Leuvenstein and
free lunch, but cheap snacks.
Leuvenstein and Williard prefer that nomenclature for describing arbitrage conditions. So what this means is there doesn't exist a random variable that everyone in the market can super replicate, so at least attain that payoff, even if they've got a very negative position currently in the market. Then we go to no strong arbitrage. No strong arbitrage states that you can't construct a portfolio with zero initial cost that always stays positive and has a positive probability of a positive payoff, no probability of a negative payoff. And if we weaken that condition even further, no increasing profit is the same, except it also says that these portfolios cannot be increasing. So this portfolio with no initial cost, no line of credit, will have greater or equal value at each consecutive time step. And that's what we exclude when we talk about no increasing profit conditions. Once you've looked at this framework of arbitrage and these five conditions, the next question that arises is which of them are important for us to study? And that question is answered by the concept of a viable market. We can look at viable markets through two lenses, through the economic lens and through the math finance lens. I won't be taking questions on the economic framework for viable markets, but I will just provide a definition. So a viable market in an economic context means that a representative agent with regular preferences has a solvable optimal portfolio problem, which somehow ties to the concept of economic competitive equilibrium. So it's easy to see that in the no strong arbitrage framework, there exists this portfolio that has zero cost and can never go negative. So a representative agent would like to infinitely invest in that portfolio, and that's what we want to exclude when we look at a viable market. From a math of finance framework, if we want to talk about a viable market, we mean a market in which we can replicate and thus price contingent claims. Because we know through the benchmark approach and various other approaches that we can price and replicate contingent claims as long as there exists this thing called a numeraire portfolio. In their 2007 paper, in the most general semi-martingale setting, Carrazas and Cárdenas show that the necessary and sufficient condition for the existence of this numeraire portfolio is no unbounded profit with bounded risk. Most of math finance happens in the risk-neutral pricing framework, which means either explicitly or implicitly the assumption of no arbitrage or no free lunch with vanishing risk is made. Why would we want to be in that framework? What is valuable to us, besides the fact that we can use risk-neutral pricing? Well, we gain access to these very powerful fundamental theorems of asset pricing. What that means is if I make this no free lunch with vanishing risk assumption, I can immediately say something based on the market characteristics about the completeness of the market, which refers to which claims can be replicated. So I have to justify why I want to work in the benchmark approach that loses access to these very powerful theorems. And the question that you have to ask there is, what do we gain? Firstly, if we disregard the benchmark approach as an approach and just look at this context, it should be clear from the figure, although it's not proven, it should be clear from the figure that if we consider semi-martingale integrands, semi-martingales being the most general process for which we can construct a meaningful stochastic integral, and then we consider this no arbitrage of the first kind condition, we have placed ourselves in the most general framework for which it is sensible to study mathematical finance, at least in the framework of pricing and hedging contingent claims. There are obviously other approaches. Why is the benchmark approach so interesting? What I call here the lever is the thing that we lean on to arrive at our pricing mechanism. So it's the principal component of our pricing mechanism. What's interesting about the benchmark approach, this principal component, the growth optimal portfolio or numeraire portfolio, is in some sense market observable. And I'll happily talk about that slightly more later. And finally, why this is interesting, but this is really slightly more of an aside, is to say that if we don't concern ourselves with the existence of this equivalent martingale measure, we gain access to volatility dynamics that would exclude the existence of that measure. And that's what I'm going to illustrate on my next slide. So the goal here is to place my research, or my approximation for the stylized minimal market model in the context of the benchmark approach. Firstly, I just want to say that this equation at the top is equivalent to equation 16 in my written proposal. What I do in my written proposal is I arrive at the stylized minimal market model by placing an assumption on the drift of the growth optimal portfolio. You can of course pose it as a completely different problem. You can do a ground-up construction, and that's what Hulley and Platen do in their 2007 paper called Hedging for the Long Run. So what I've done here is we just pose this as a model for an index. So we say we're going to model this index as something where its volatility feeds into its drift in a squared way. One of my professors is very fond of quoting one of his professors, who always says that once you've written down an equation, you must stare at it until it speaks to you. What does this equation tell us without doing any analysis? The first thing that we can see here is this thing, given that we know the dynamics of the risk-free rate, is completely parameterized by its volatility. That's the sense in which I mean that, in some sense, the growth optimal portfolio, if we can approximate it in the market, will reveal to us something about this volatility structure. The second point that I want to mention here is, in my proposal, I take the approach of showing that no equivalent martingale measure exists for this process, if you define this process as your index price process. And I do that by showing that this is equivalent to a time-transformed squared Bessel process of dimension 4, which we know from the properties of Bessel processes to be a strict local martingale. But there is an intuitive way to see by this structure that you can't achieve an equivalent martingale measure. So, what we see here is this volatility can grow without bound as the stock price decreases. Stock price decreases, volatility goes up. This is also known as the Lieberich effect. This would indicate that perhaps this process can achieve negative values, but the volatility is feeding into a squared way into the drift. So as the price process decreases, the volatility increases, but the drift becomes largely positive. Under P, you can show that this thing has a zero probability of attaining zero. Now let's hypothesize a possible risk-neutral measure. We know that under the risk-neutral measure, we want this process to drift at R. What happens then is we have a linear drift, but we still have this exploding volatility. And it should be intuitive that that means we can attain zero under this hypothetical risk-neutral measure. So you have two measures, one in which your process can never attain zero, or attain zero with probability zero, so almost surely never attain zero. And you have another measure where there is a positive probability of the process attaining zero. It's clear to see that those two measures can't be equivalent. Having established the stylized minimal market model, we can now begin to discuss how would we go about simulating this SDE.
Just one point. If theta is very small, theta squared is even smaller, huh?
Absolutely, yes.
So how do you then explain that the process is positive?
If theta is very small, theta squared is even smaller, so you don't have this large drift. But for theta to be small, obviously you are constrained somewhat in your assumptions on alpha and on eta. But if theta is very small, that means we're probably not in a low stock price situation. So we'll stay positive even if the volatility is small.
I just need to reinforce that point though. There is, the failure condition, from what I understand, needs to be met in order for it to not reach zero.
Absolutely.
So that's another element that you have to...
You've also got a strictly positive drift. So if theta is very small, it's drifting upwards anyway.
Also what you can do is there exists a closed form solution for the transition density of this process. And if you examine that transition density, you can see that you've got a zero probability of attaining zero.
But only under the failure condition.
Yes, only if the failure condition holds, that is indeed true. What I just want to say before we move into this framework of numerical methods is there are really two approaches to simulating this process, a top-down and a bottom-up approach. So the bottom-up approach would be we concern ourselves only with this, which is a generalized square root process. That means it's connected and similar to the CIR process, but it has time-dependent coefficients. Or, because we know this thing is a squared Bessel process of dimension 4, we can actually go and do an exact Monte Carlo simulation for squared Bessel processes. That's possible, although it's difficult, and then you can use the transform to arrive at this process. This classification of the available numerical methods in mathematical finance is my classification. Of course, it's definitely not unique, and it's definitely not the final word on how you can divide these models. In each of these subcategories, there are definitely methods that could be moved to another category. We're going to begin with Monte Carlo methods. Monte Carlo methods we're all familiar with, and they concern themselves with being able to sample from some sort of distribution to generate the path of the process. They can be further divided into exact, or as Tom likes to call them, long step, and approximate or short step. An exact Monte Carlo simulation refers to the fact that we have access to the transition density of the process. So that means if I know S at t now, I know the distribution of S at t plus delta t, regardless of the size of delta t. The way I like to view an exact simulation for Monte Carlo is if I generate a path for which I know the transition density, that path could be a true realization of the process. It's representative of the process. An approximate simulation concerns itself with discretizing this SDE. These are Euler-Maruyama. There's a slew of them which I can't call to mind right now. Milstein, and higher order methods. Of course, an approximate solution can run into problems and not be representative of the stochastic differential equation. So if you do an approximate method for the CIR, you might have this path that goes negative. You can even take this approximation slightly further and say, well, because we're doing an approximate solution to this SDE, I'm not going to concern myself really with sampling from, in this case we have a normal distribution, a scaled normal distribution, but you could approximate that distribution by saying all I concern myself with is the mean and the higher order moments. So one of the examples that Plato uses in his book is to say that if we want to break this thing into an approximate solution, I don't have to concern myself with sampling from the normal distribution there. I could use a two-point distribution that matches it in mean and in the variance. So in the exact framework, your error is bounded by the number of samples that you use. In the approximate framework, you have to be careful because you're introducing two sources of error. You have the sample error, how many paths are we simulating to approximate this integral, and you also have this error that you're making in the discretization. So that's slightly harder to quantify. I'm then going to jump briefly to integration methods. Again, this is a somewhat arbitrary classification. I'm capturing here quadrature and transform methods. Quadrature methods concern themselves with coming up usually with some optimal discretization of the unit cube into a finite space, mapping that unit cube onto the integration bounds, and then solving the integration. Transfer methods, Fourier methods, cosine methods, convolution methods. They essentially allow you to solve that integral through a transform. What's important to mention here regarding transform methods is that for most of these, as far as I know all of them, but I will stand to correction, you need to know the characteristic function of the process. Lastly, we arrive at lattice methods. This is not lattice methods in the strictest mathematical definition of a lattice. What I consider lattice methods here are methods that discretize both space and time. The most famous of these, of course, are finite difference methods, and they're not subset, but I'm going to go less used cousin, tree methods. Although finite difference and tree methods both concern themselves with solving the same problem, essentially what is the price of some contingent claim at some time, the approach that they each use is quite different. To apply a finite difference method, what you want is you want some partial differential equation that either explains the time dynamics of the underlying or explains the time dynamics of the price process. For a tree method, you have some lever or pricing mechanism that you want to be true at any node in the tree. Tree methods are in truth Markov chains. If we have this whole slew of numerical methods, why do I want to study trees? The first point that I'd like to make, and I caveat this by saying my review of the literature shows no unified framework with which we can study trees. We generally view trees as some idiosyncratic construct that we make in math finance, but really trees are discrete time Markov chains. And all the proofs, or the proofs that are most commonly cited to show that these trees converge to the true process, are done in the framework of stochastic control, discrete time Markov chains, by Harold Kushner. And this has been done for almost 30 or 40 years. Because there is this lack of unified presentation, I believe that there is this view that we don't have the same tools, mathematical tools, to analyze trees. And that's not true. We actually have access to all of the tools of discrete Markov chain analysis. I see that as a gap in the literature and something that I would like to address. Secondly, although they're often scoffed at, you cannot immediately say that trees underperform other methods. Trees are especially good at two things. One of them is if you create a tree for some underlying process, once that tree construct is in place, it is essentially free to price any derivative on that tree. If you don't concern yourself with that, another thing that trees are specifically well suited for is being constructed in such a way that they optimally price a certain derivative. And an easy example of that, for instance, is a barrier option. You can align the nodes of the tree with the barrier so that you don't introduce option specification error, which means you're pricing it truly at a different barrier than is specified in the contract. Option specification error was identified, or was called option specification error, by Derman and his compatriots in 1995. And that's also where he provides his method for constructing trees in that way. Finally, I have historical reasons for wanting to look at trees. Essentially, the benchmark approach can be considered as a paradigm shift away from risk-neutral pricing. I can't speak for everyone, but when I was taught risk-neutral pricing, I was taught it on the basis of a one-step binomial tree. It is indeed possible to present the growth optimal portfolio and risk real-world pricing in that way, to construct a one-period binomial tree that illustrates that pricing concept. But I believe that it's not sufficient until you can also say something about the optimal way to construct the entire tree. Finally, I want to talk about my first attempt to solving this problem. And I'm looking in the framework of vector quantization. Vector quantization has been around since the 1940s and is very widely used in signal compression. If you've ever used an audio codec, if Windows Media Player has ever complained that you don't have the correct codecs, those codecs were in some sense using vector quantization. I just want to state here in the simplest way the problem that we're trying to solve. We have some, I'm going to say it's d-dimensional random vector, it can take on infinitely many values. So in one dimension you can consider a normally distributed random variable, it can go from negative infinity to positive infinity. We want to approximate it by a discrete random vector on some set of finite cardinality. So the problem that we're trying to solve, generally in math finance, is this expectation, some functional of a random vector, some function of a random vector, and we're going to approximate it using this sum. And the question that we're trying to solve is, what is the optimal way to place these points? In Monte Carlo, we sample those points and we drop this probability, but I want to do this in a completely deterministic way. I'm going to state it now slightly more rigorously in mathematical terms. We're going to measure optimality here by considering the error between the true random vector that can take on infinitely many values and the projection via pi of this random vector onto gamma, where gamma is our set of cardinality n. We want to minimize this measure. Generally we are concerned with the L2 norm, or the L2, you can generalize it. So the two unknowns in this equation that we want to address is we want to address pi. What's the best way to project this vector? And we want to address gamma. What's the best way to discretize that set? It can be shown that the best way to project this random vector is always what is known as nearest neighbor mapping. So that essentially has to do with constructing the Voronoi partitions of gamma, and the Voronoi partition in 2 dimensions is just some pentagon or hexagon based on where your other points are, some shape, and everything that lies inside the Voronoi region, any random vector that occurs inside that Voronoi region, we're going to map to the point that generated the region. If this is optimal, then we know pi already, and we need to concern ourselves only with gamma. This is the error function. When we know that the projection that we're going to use is Voronoi projection, this becomes known as the distortion function. Doing this, there are a lot of mathematical techniques, but doing this essentially comes down to finding some sort of, generally comes down to minimizing the distortion. And it turns out that the optimal way to do that is by setting the gradient of the distortion to 0. It's not as simple as a first order approximation, but that's what it realizes as. So the problem becomes a root finding problem. In 1 dimension, we can use Newton-Raphson to try and solve this root finding problem. In higher dimensions, we have to use what are known as stochastic gradient algorithms, or competitive learning vector quantization. And essentially what that means is we take a random set of points, we sample from our distribution, and every time we pull a sample from our distribution, we shift the point nearest to it slightly towards that sample. So what that means is you end up with an optimal set of points somehow located to the points that have high measure. This is a computationally very expensive process. Even in 2 dimensions for the normal distribution, this is slow. You're essentially doing a nearest neighbor mapping on a set of cardinality n, and there are various algorithms for speeding up nearest neighbor, but nearest neighbor is not fast mapping. Until this year, it wasn't useful for solving stochastic differential equations until the invention of this technique known as recursive marginal quantization. I offer this reference because this reference is not in my proposal. Recursive marginal quantization, which is a technique I'm still working to understand and implement, essentially says that if we approximate our stochastic differential equation using Euler-Maruyama, and we find the optimal discretization of that process at the initial time, we can use that optimal discretization via a transform and step it through time, instead of having at each time point to resolve that problem. This seems like it lies firmly in the integration methods framework, and obviously I'm looking at trees. There has been some work done, and what I will do is, if we know how to optimally discretize a distribution in this sense, that gives us information about the optimal placement of tree nodes. And that's my current work. Thank you.